Welcome to the mole. Now this is just an introduction to the mole, and we're not going to go into too much depth with it. But, so since atoms and molecules are so ridiculously tiny, that means that counting them becomes too difficult to become practical. So we have a similar problem when we have other objects that we want to count, like jelly beans. If we have a large number of jelly beans, we don't want to have to sit there and count through each and every jelly bean. So we resort to counting by weight. If we know the mass or the average mass of a jelly bean, then if we measure the mass of the whole bunch, we can calculate or estimate how much or how many jelly beans the whole sample has. So, for example, if we know that each jelly bean weighs 5.0 grams on average, then we know that a 500 gram sample contains 100 jelly beans. And we can scale this up if we want as well. So, the number of molecules in a glass of water is in fact so large that it becomes cumbersome to refer to the actual number. Now, so we created a unit. We create a unit that's similar to the unit of dozen, only much, much bigger. So, we use a mole, M-O-L-E, and we abbreviate it M-O-L. Not much of an abbreviation, but it's something. So 1 mole is equal to 6.022 times 10 to the 23 objects. It's 6.022 times 10 to the 23 of something. Just like a dozen is a dozen of something. It's 12 of something. Right? It's a dozen donuts, or a dozen rabbits, or a dozen people. A dozen carbon atoms, let's say. So we have a mole. We have a mole of rabbits, or a mole of donuts. That would be tasty. A mole of people, or a mole of carbon atoms, let's say. So, if we have 6.022 times 10 to the 23 molecules of water, that means that we have 1 mole of water. So now we have a way of talking about ridiculously large numbers of molecules, but in relatively small quantities, right? Or rather, we can change the number from 10 to the 23 to 7, let's say, right? So we don't have to be using scientific notation to talk about numbers of molecules. We can use moles instead. So for reference on how big this 6.022 times 10 to the 23 number really is, on Earth there are approximately 1.4 times 10 to the 24 milliliters of water. Now, 18 milliliters of water is 1 mole. That's not a whole lot. Now, that means that in that 1.4 times 10 to the 24 milliliters, divide that by 18, and we get 7.7 times 10 to the 22 moles of water. But that means that in all the oceans, all the lakes, all the rivers, all the frozen water in our glaciers and ice caps, we only have 7.7 times 10 to the 22 moles of water. So we don't even have 1 mole of moles of water on Earth. We have about 1/8 of that. We have 0.12 moles of water. Now, that's only 18 milliliters of water. So we don't even have a mole worth of 18 mils of water. That is tiny. We have roughly 1 mole's worth of milliliters of water on Earth. So, that's a huge number. 6.022 times 10 to the 23 is a very, very large number. So, when we use the unit of mole, we have to specify what it's a mole of. So we have to say something like 2.5 moles of carbon atoms, which may be abbreviated like this: 2.5 moles of carbon, moles of C. But we have to specify what it is. We can't just say 2.5 moles. It doesn't tell us, well, moles of what? Is it moles of water molecules? Moles of oxygen atoms? Carbon atoms? Is it moles of rabbits? We have to specify moles of something. So when you're writing down your number of moles in a calculation, you should always be writing down moles of something. Now again, you can abbreviate it like this: 2.5 moles C, or 2.5 moles oxygen, or 2.5 moles acetic acid. That's fine as long as you identify what it is that you're measuring moles of. So there are approximately 0.0000017 moles of insects on Earth. That's 10 to the 19 insects, or thereabouts, which is 10 quintillion. But that's nowhere near, that's far, far less than 1 mole. We don't have a mole's worth of insects on Earth. And there are a lot of insects on Earth. So, a mole is really, really big. That's a very, very large number. So, that was an introduction to the mole.